Thank you. Nice to be here. And so the title of my talk will be Twitter Heron in Practice. How many of you know about Twitter Heron in the first place? Okay, not many, looks like. Considering the fact that the paper has been downloaded close to 18,500 times. Okay, so I'll be giving a kind of a little bit overview of what Twitter Heron does. And so feel free to ask me any questions that you might have, because I have a lot of details in my head, but unless you ask me questions, then only the details will come out, you know. So anyway, so with that short introduction, I will be delving into the talk. So the talk outline goes as follows, and initially I will give an overview about what Heron is, and we are kind of introducing the notion of what we call as a micro-streaming engines, and then I will discuss in detail a couple of problems that we face when Twitter Heron is running at a large scale for the last 2.5 years. And then I will delve more detail into what are the resource consumption of Heron itself, and finally I'll do the conclusions. So as you all know, Twitter is all about real-time, and we do a lot of real-time processing, and that includes computing real-time trends based on analyzing the tweets, what is the emerging news that is coming out, and also there are a lot of real-time conversations. So millions and millions of real-time conversation flows through those tweets, and in order to identify and bubble up those conversations, we need to employ real-time processing. And also we do real-time recommendations. When we inject an ad, we inject into the stream depending upon the context, and those contexts are continuously computed and the ad is injected in real time. And finally, we also have real-time search, where the tweets have to be indexed the moment it arrives within 100 milliseconds, so that the results of the search can include the newly or the fresh tweets as well, so that it feels very close to real time. So which means we are collecting billions and billions of events, and how to process these events in order to provide all these various different real-time processing is a big challenge for us. And initially, as you all know, in 2011 we open sourced Storm, and Storm was one of our mainstay for the from 2011 to 2013. Then we faced a lot of issues with Storm. I would suggest, like, I'm not going to reiterate all the problems that we faced with respect to Storm, but I would suggest to read the paper that I will point out to the paper, and please read about it if you wanted to know more about it. And so I'm going to jump directly into Heron itself. So just to give an overview of Heron, I will introduce the Heron terminology. And the Heron terminology we just borrowed from Storm, and to keep it simple, so it's the notion of a real-time job is called a topology, and a topology is nothing but an DAG, and the vertices of the DAG represents the computation, and the edges of data, the edges between the vertices are essentially streams of data tuples. And there are two types of vertices, the spouts, and spouts essentially, like, what they do is they tap into the data source and extract the data and inject the data into the job itself. And some of the examples include Kafka, Kestrel, and how many of you know that Twitter has open sourced their new queuing system or messaging system called the distributed log? Okay, there you go. So it's pretty very good. It has been in production, like 60 or 70% of our topologies are running in distributed log now. And so it doesn't mean that we have to stick with only messaging systems, but also with the MySQL and Postgres and a very few others as well. The second one is bowls. And the second type of vertices is called bowls, and bowls are essentially represents computational elements where you process incoming tuples and emit outgoing tuples depending upon how the processing goes. And some of the examples include filtering, aggregation, join, or any arbitrary functions. So how does a Heron topology looks like? Like, you have a couple of spouts feeding into the next stage bowls, which are like bolt 1, bolt 2, and bolt 3, and they in turn feed to the next stage of bowls, bolt 4 and bolt 5. And one of the biggest differences, like compared to MapReduce, is the fact that there is no limit to the number of stages that you can stitch to. You can stitch as many stages as you want. We have jobs internally that is running like more than around 10 stages or 15 stages. That's common. So the word count, to give a concrete example of how a topology looks like, let's take the example of a word count where you are counting the stream of words that are coming out of tweets. So in order to accomplish this, you need a tweet spout, which in turn taps into the Twitter feed, and that tweet spout will pass the entire tweet into what you call a parse tweet bowl, which is responsible for breaking the tweet into a smaller set of words. And finally, you have a word count bowl, which in turn counts the distinct words that is occurring across the tweets, so that you can spit out the count in a periodic fashion. And from a database parlance, we call this as a DAG or something called a logical plan. And but in reality, when this topology runs in physical machines, it's a completely different ballgame. Reason why is like you might not be able to process the data in a single process or even a single machine. And because of that, like you end up having multiple instances of each one of those elements in the DAG. So the way the same topology will work in the physical machines is like you have tasks. So you have the tweet spout task, which are several of them, and similarly there is a parse tweet bowl task, which could be several of them. And you can configure each one of those stages or each one of these nodes in the DAG by using a parallelism parameter. So, and you have a word count bowl tasks as well. So now all these tasks could be distributed across all the machines, and they will continue to run. And the size of your number of tasks is proportional to the amount of data that you wanted to process at every stage. Now, one of the main issues is when a parse tweet bowl emits the data, on one of the tasks emits the data, which task in the downstream it has to go to. So that is where the notion of stream groupings come into play. And so first is shuffle grouping. You have a random distribution of tuples, and it can go to any task downstream. And the fields grouping essentially takes the fields of some of the tuple and groups them, and based on the value of the fields, it picks up the task downstream. Then the third aspect is called all grouping, which is replicates the tuples across all the tasks. And finally, like you have this global grouping, which sends the entire stream to one single task. So most of the time, probably like 95 to 99% of the time, you use a combination of shuffle grouping, fields grouping, or one of those. So now getting back to the word count topology, how do you annotate the topology with the grouping information? So as you can see, from a tweet to a parse tweet bowl, the tweet can be processed by any parse tweet bowl, which means a shuffle grouping will suffice there. On the other hand, when you go from a parse tweet bowl to a word count bowl, you should be doing fields grouping, because you want the same word from across different tweets to be end up in the same task. So with this introduction, I'm going to move into why we did Heron when we had Storm in the first place. So there was a lot of things that we looked up, and especially after operating Storm on several thousands of clusters. So what we did is like one of the major issues was performance predictability. So it was Storm was having issues in terms of how to predict the performance from an end-to-end point of view, as well as the individual bolts and tasks and all the various stuff, right? So how do you have a system where you can predict your performance? Second one is like improve developer productivity. So we found that Storm jobs are very challenging to debug, and that caused a lot of developer productivity in terms of trying to figure out a needle in the haystack, where what bolt and what instance of the bolt and on what machine it is running is causing issues. How do you improve those? So how to improve the developer productivity such a way that you can quickly get your bugs fixed and move on. And finally, like ease of manageability. I mean, one of the major things that we had with respect to Storm was we were running on different cluster on its own. And so whereas we wanted to, as a team, we don't want to maintain our own clusters and everything. Instead, we wanted to kind of run it alongside the critical services that serves Twitter and all the other services, and it should be running as a part of those big clusters that we have, so that we don't have to manage clusters and all the various stuff. So that ease of manageability and the developer productivity and performance predictability are the three main reasons why we started doing Heron. So now, what are the Heron design decisions? First of all, it should be fully API compatible with Storm. And the reason why we ought to be API compatible with Storm, there are a lot of legacy code that has been already written on top of it, and they are all in production. And we have to make sure that we can migrate them seamlessly without having to do anything at all. So without any code changes and any developer's time. So which means the notion of a DAG applies, topologies, spouts, and bowls apply, and all the APIs are compatible. The second aspect was task isolations. So we wanted to have the notion where each of the spout and bowls are running on a task of its own or a process of its own, so that you have the ability to do profiling and doing resource isolations and all the various other aspects that comes along with it. So then finally we used mainstream languages, which is like C++, Java and Python. So because the team was, the Storm was written in Clojure, we did not have enough tools for that language in order to make the development as fast as we could. So hence we resorted to writing some of the critical components in these mainstream languages. So any questions before I go further deeper into Heron? Okay, cool. Hope I'm very clear. So anyway, so the first thing design is like we got away from a scheduler. So as everybody knows, Storm had its own set of scheduler for scheduling tasks in a cluster of machines. So we moved away from it. The reason we moved away from it is because the scheduler have their own set of communities like Apache Mesos, Yarn, and then there are some frameworks that are developed on top of these schedulers, Apache Aurora, then Marathon, then we have ECS, which is Amazon Docker Container Service. There are so many of them. So instead of introducing yet another one and adding into the mix, instead what we did is let's take a piggyback on an existing scheduler, and so whenever you submit a topology, it looks like yet another job for the scheduler, so that it can schedule the topology also alongside with other jobs. So that's what we did. So any topology that you submit goes to the regular schedulers, and that in turn gets the resources that each topology wants it, and each topology is run as a separate job. So if you look at how the entire topology runs, so we have this notion of a topology master, which is responsible for the life cycle of the entire topology, and that is running in a special container called the container 0. And when I say container, it's nothing but a C group container that Linux supports, so which allows you to have a nicely resource isolations, and so that whatever the resources that you allocate for that container, like X CPUs and Y amount of memory that you would like to allocate for the container, does not get exceeded. So that when multiple containers are sharing the same node, you don't exceed your quota, so that it does not affect any performance of the other topologies or other services that are running alongside in a multi-tenant cluster. So the topology master runs in a container 0, and the topology master comes up first and looks at its DAG and finds out how much resources that it needs to allocate, and requests that much of resources from the scheduler. And the topology also saves its state, which is essentially the DAG, and some of the execution state, which includes who launched the topology, what time it launched, what version of the Heron it is running on, all kind of various stuff, which is called the execution state, is all returned into a Zookeeper cluster. The reason being it's returned into a Zookeeper cluster is the container 0 can fail, the topology master can fail in a distributed system. So which means like if the container 0 fails and the scheduler moves the container to somewhere else, that container will come up, and the topology master will come up again and will pick up the state from the Zookeeper, so that it doesn't lose any state. And the topology master is not even involved during the data path. It just is involved only in the control path. As long as any changes in the physical plan, logical plan is stored, that is the state it maintains. So then once the resources are acquired from the scheduler, then these containers are scheduled by the data containers are scheduled by the scheduler itself, and each of these containers contains something called a stream manager, and there is a notion of a metrics manager, and there are I1 through I4. These are all nothing but instances, and these instances are the ones that run your spout task and the bolt task. Remember I was mentioning about the word count topology, which contained the tweet spout and the parse tweet bolt. Those tasks run in these instances I1 through I4. And the stream manager is responsible for moving the data around across the containers. So essentially when data is emitted from these I1 and I2 and I3, so data gets into the stream manager. From the stream manager, it goes to the other stream manager before the data is delivered into the other instances. So even if the instances in the same container want to exchange data, they can bounce off from the stream manager as well. So you can think about stream manager as what you call as a data router. So where it routes the data to the appropriate task from its source. So that's what it does. And the metrics manager essentially is one that collects all the metrics coming out of these various instances. And the number of metrics that we collect is so huge. I mean, because whenever some topology goes into some kind of a state, we need to know what happened with the topology right away. So because of that, we collect several hundreds metrics about the topology, including how much tuples it has processed, how much bytes it has processed, what is the latency it experiences, how much bytes it pushed into the stream manager, all kind of statistics, whatever you can think of. And how many times the container got killed and rescheduled, how many times the process got restarted, all kind of statistics like that is collected, and those things are sent to an offline system. So, huh?
Can I ask a question?
Sure.
Number one, container, is it a Docker container?
So it could be mapped to a Docker container, but in production we don't use Docker containers. Instead, we map a container to a Linux C group containers.
Gotcha.
Yes.
In terms of metrics, it will be interesting looking at it from a whole task from end to end. And the metrics kind of collecting those
Yes.
observations. Do you have a way to cross-correlate across containers? Or
So like currently we aggregate the information coming out of those containers. But we have information about every spout and bolt and all the various informations also is available. So that you can look at whether a particular spout is the one that is causing the issue or a particular bolt is causing the issue. You can do all of them.
yeah, but you can correlate that to the application that you are running.
No, this is only for operations. Yes. So there are some user-defined metrics. For example, as a user of a topology, where I am interested in collecting some metrics, you can do that as well, which is called user-defined metrics. We also allow that, and that metrics also is pumped to wherever you tell it has to go to. So that also we do that. But for operational purposes, we collect hundreds of metrics so that if some topology that is in production, they come running to us, hey, there's something wrong with it, we should be able to locate the problem very quickly enough so that you can turn around quickly, right? So, yes. So.
I'm thinking along the line of Zipkin kind of.
Yeah, Zipkin is for tracing, but this is more online. Immediately you can check the metrics itself, yes. So then when the topology actually gets executed in the physical nodes, so this is what you will see. So you have these 4 containers, and some of the instances of the bolts and the spouts are running in these containers, and you have this notion of stream managers in this container, right? Now what happens is once these containers come up, the stream managers interact, or rather they do a fully connected graph where each of the stream manager connects to the other stream manager, and that's the only way they can start exchanging data right away. So any data that is put into the topology from the spout S1 on the top left container will get into stream manager before it goes to the other stream managers. And the advantage of using stream manager is several aspects. For example, it reduces the number of resources in terms of the sockets and ports from order of n squared to order of k squared, where k is the number of containers as compared to k is where n is the number of instances of various spout and bolt who directly connect to their respective downstream components, right? And another advantage of isolating the stream manager code is you can write any kind of processing semantics that you would like to. So it's like, for example, at least once, at most once, exactly once, and you can even make one stream manager for each one of them. So some of the Heron topologies that we're running include the shapes of this form. So you have a simple topologies to all the way to complex topologies, as I mentioned, and some of the topologies are generated by a hummingbird, which is a Scala interface that we run on top of Heron. Heron you can think about as an engine, and hummingbird is the API that we use, and that API in turn generates these several topologies, complex topologies. Some of the topologies that are smaller, or these ones are directly written on the Heron API itself. So yes.
So the target that must be instantiated ahead of time.
Yes.
Before you can do any computation.
So the topology, the DAG shape should be instantiated. The DAG, like for example.
Resources also assigned.
So resources can be assigned dynamically.
Okay.
So like when the topology master comes up, you can tell I need this many containers, right? Yes. But the DAG itself has to be instantiated because that is contains the processing logic, right? So Heron at Twitter has been in production for more than 2 years now, and obviously I can't tell the exact numbers, but we are processing tons of data, and probably like the number of nodes that are running in Heron is like probably a few thousand nodes. So it's all fully running Heron itself. So some of the use cases at a high level is real-time ETL, real-time BI, and product safety like fraud detection, spam detections, and all the various stuff, and computing real-time trends, and real-time ML in terms of model building and model enhancements. And we also do some kind of real-time media as well in terms of processing and real-time ops. Some of the operational data is continuously processed in order to spit out some analytics, and based on which quickly decisions are made. So these are some of the high-level use cases. And so I'm going to delve into more of a couple of problems that we kind of solved in production, and I just want to highlight those things with that short introduction to Heron. So the first thing is componentizing Heron. So I mean, the big data ecosystem is continuously evolving. A lot of new technologies coming in and going away and all this stuff, right? So as you can see, the heterogeneous system with respect to Heron at least is there are multiple several schedulers, like managed schedulers, unmanaged schedulers, then the state managers, which could be a Zookeeper or even a local file system or even a Hadoop, which provides some kind of synchronization mechanism. And the job uploaders, once you have your jar, how do you upload that jar, right? That could be anything from an S3 to a local file system or even Hadoop in this case. So this ecosystem is continuously evolving in some fashion or other. So how do you design a system such that your dependencies on this ecosystem is minimal and the core does not change enough and all? So when we did that, like we looked back. I mean, one of the things that I always believe in is the computer science revisits itself in every 20 to 30 years in some fashion. So I said, okay, let's go back and look in what people have done in early stages, right? So one of the things that we came up with was like microkernels. So there was a notion of monolithic kernels where everything was written as own single software. That's what used to be the state of the art at the time. So where you have the hardware, device driver, scheduler, virtual memory, then IPC file systems, and even a virtual file system on top of it on where the actual file systems are mapped. And they saw that why you have to do a monolithic. Instead, they took only the necessary pieces and moved everything to the more at the application level. So that's what called the microkernel. And microkernel has the hardware and the basic IPC and a few things, and the rest of them are things were moved to the more application level. And we kind of were inspired by that, and Heron design also follows that. So we have the basic, in streaming, any of the streaming, the basic thing that you require is the IPCs, essentially a way to communicate between processes in some fashion, running on top of hardware. Then everything is the modules, like everything is a process and modules that you written on top of it. So what happens is like you can go and replace anything you want. I mean, like for example, I want to write my own high-speed instances and everything. All you need to do is instance interact with Stream Manager through a protocol, and as long as you can implement your protocol, then you're done. You can write your own instances as well. And similarly, you can write your own metrics manager. Already we have written metrics manager that can go to send data to Scribe as well as Graphite and all the various stuff. And whereas the Stream Manager also can be replaceable because of the plug and play kind of architecture. And Topology Master's logic, where you wanted to do something cool, you can go and add that as well. So essentially, like every component is replaceable in some fashion or other. So we don't call Heron as a streaming engine anymore. Instead, we call it as more of a streaming framework where you can add your functionalities that you like to. So what are the advantages of this architecture? It's plug and play. As the environment changes, code does not change. And also like multi-language instances is possible, because today like some of the multi-language related API, they don't run in native language instances. Instead, here you can write your own instance. For example, today the supported API uses Java API, so which means we have a Java instances. And if you want to write a Python API for writing your topologies quickly enough, then you can write a multi-language, one of the instances like Python instances, and boom, then the Python code will execute in the native Python interpreter, as compared to you having data coming from a Java process into a Python process so that it can execute. All those other stuff you don't need to do actually. In fact, like there is some work going on already to write a Python instance as well. So then multiple processing semantics that you can support. Then similarly, since it's all componentized and multiple team members can work on individual components separately, and it's very fast for development as well. So the Heron environment. So as I said, like we have multiple environments for Heron within Twitter itself. So for example, our development environment uses a notion of a local scheduler where you can bring up entire Heron running topologies into the single laptop. And it also uses a local state manager, which is essentially like a synchronization mechanism. And for that, we use the local file system and a local uploader, where again, we use local file system to upload your jobs and run it. And that is when our primary, what you call a development environment, where we iterate very quickly, fast enough. And it runs as though it is running on a distributed system itself. So it's easy to, for example, if I introduce the bug in Stream Manager, then I can just GDB into the Stream Manager, boom, and I can debug that right away. So it's very fast and easy for development. Second one is like for cluster and testing, we run it on Meso/Aurora scheduler, and with Zookeeper as state manager. Then we use HTFS for the uploader, and that is used for testing purposes in a distributed systems. And our production runs in Aurora scheduler, which is the managed scheduler that is written on top of Mesos. And we have a Zookeeper state manager and the Packer uploader. Packer uploader essentially manages versions of topologies and all the various things. For example, your topology might go through various versions depending upon the functionality, bug fixes that we've added, and it can manage the versions of the topology as well. And that's what runs in production. So within Twitter context itself, we have multiple environment. And there are other groups which have taken Heron and running it on AWS as well. I've not included them, but they're running it on top of AWS as well too. So now why Aurora? I mean, Aurora has been one of the very widely used scheduler within Twitter, and it manages hundreds and thousands of machines. So a lot of critical services run on top of Aurora itself. So the Heron runs in the context of Aurora in a multi-tenant cluster alongside with the other critical services as well. So then it allows you to provide authorization and expressive DSL to write your jobs. And it's also very high availability and scalability because there's a team behind it which manages the whole show for Aurora, and a lot of inbuilt metrics for monitoring and debugging as well. So with that short discussion about componentizing Heron, I'm going to go into the next problem that we face in production. It's called stragglers and back pressure. This is a very interesting topic actually. So stragglers are the norm in a distributed system. When you have a distributed system, there are several reasons why some process might be slow. I mean, especially some process that is running a part of as a single job could be slower. There are three primary reasons for it. One is a bad host. Like 80% of the time, we say, hey, by the way, like the machine that the job got scheduled is bad, because it could be having some RAM errors or some disk errors or whatever might be the case. Especially when you're running on a few 100,000 node clusters, some bad apples will pop up here and there. So that's a commonly observed problem why stragglers start occurring. The next one is execution skew, which is essentially like a manifestation of the data hitting one process, a lot of data hitting one process because of the hotkey problems. Then the third one is what we have seen is inadequate provisioning. So if a job requires some X amount of provisioning in terms of resources, but you're not given the enough X, stragglers will start occurring as well. So now what are the approaches to handle stragglers? So the first thing is send us to, whenever a straggler occurs or whenever there is a straggler in your job, you can send data to that straggler, but it will slow down everything. So now the simple strategy is when the sender figures out I can't send as faster to the receiver, which is the straggler, I simply drop data. So that is one approach. The second approach is slow down the senders to the speed of the straggler itself, so that everybody is going at the pace of the straggler. So in this case, there will be predictability and accuracy and all the various stuff. And detect stragglers and reschedule them. So like proactively detect stragglers and reschedule them in some form or the other. So the drop data strategy. So what happens with the drop data? So it's very unpredictable. So if the machine is going really slow, you can continuously drop data, and there are instances that we have seen is 2 to 3x inaccuracies. So for example, Storm was doing this drop data strategy. With that, what happened was like when the data was being shared with some of the potential partners, they saw 2x to 3x inaccuracy during certain times. And that became affects accuracy quite a bit, especially if you're trying to share some essentially critical data. And also it gives poor visibility in terms of where it is being dropping and all this thing, because especially if a job is running on a few hundred machines, how do you know which one the guy is dropping data, which is very difficult to locate it. So the slowdown sender strategy. So in this case, it provides predictability, and depending upon how the stragglers or the stragglers are not present, it processes the data at the maximum rate and also reduces recovery times. Whenever some thing fails, immediately it will pick up, it gets rescheduled on a different node, and it is going really as fast as it can. So then it can nicely handle temporary spikes. So if you delve more into the strategy, essentially let us take a simple linear topology which has a single spout, followed then in turn goes into a bolt B2, and that in turn feeds into a bolt B3 and another one bolt called bolt B4. Now, so as I said, like there are 4 containers that are running these spouts and bolts, and you have these stream managers which are running in those containers, and they are the ones which are providing the data path for exchanging data. Now let's say, for the sake of discussion, the B2 is going slow, and the moment when B2 goes slow, the stream manager detects that the B2 is going slow, then it will send that what do you call initiate back pressure or initiate like a slowdown strategy to all the other stream managers. So now the stream managers, when they look at their instances on this respective containers, and when they see a spout, they say that we are not going to accept any more data. So what we are trying to do in this strategy is like the source of the data is the spouts. So if you're not taking any more data from the spouts, then the pace of the topology could be controlled, right? So by choosing when to pick up the data and not to pick up the data, you are going at the pace of whatever the straggler is. So which means everybody slows down. So everybody slows down to the pace of B2. So now when B2 picks up speed, then everybody will start picking up speed, because there will be another message that sends out saying that, hey, by the way, back pressure is relieved, everybody can go at a high rate, right? And the way we do that is we have what notion of a watermark, high watermark and low watermark in buffers, and by using those watermark buffers, you can adjust when to kick off the back pressure and when to relieve the back pressure. So the back pressure in practice, when we looked at it, like so if back pressure is kicking in so heavy, then you will fall back in the read part of it, because you're pushing the back pressure to the source. Now once you hit the source and if the source is not consuming enough data, then you know clearly that you're falling behind. And one of the measurements that we make is the lag. So how much is the read versus the write lag is there, and that is proportional to the whether the topology is going at the input rate or it's lagging behind. So that is a measure that we use in order to figure out if there is any issues in the topology or not. So if that is the case, sometimes what happens is the back pressure might not recover. So we manually shoot down that container, and the container gets rescheduled, automatically restarts. So back pressure in practice. So most of the scenarios, back pressure recovers and without any manual intervention, and which is a nice thing. And there are some instances where we face sustained back pressure, and that's partially attributed to bad or faulty host and irrecoverable GC cycles. So one of the things that we are looking at into it right now is doing anomalies detections within these containers and the spout instances and all the various instances, so that we can detect this bad and faulty host. Then we automatically shoot down that container so that the container gets rescheduled somewhere else without any manual interventions. So that is the problem that we are looking at in detail. And sometimes users prefer dropping off the data. So some people say, no, I want to be at the top of the queue always. If the processing is not done on time, we might lose some other result, but I don't mind being inaccurate. So for that, we use sampling-based approaches. So since, then how do you detect bad and faulty hosts? We use another Heron topology to detect them. So the hundreds and thousands of machines that are there, and we have a Heron topology that detects those data coming from those and analyzes data, see whether that topologies are not topologies, any a bad host is present, then you go and put the feedback and take it out, that machine out of service. So I'm going to skip the load shedding section, and instead I'm going to go into what do you call the resource usage of Heron. So one of the things that people have talked about is, yes, can I keep the question a little bit later? I have only 5 minutes. Okay, so yeah. So the Heron resource usage, we took a 2-node topology. One is the event spout and another is an aggregate bowl. And the event spout takes 60 to 100 million tuples and filters the tuples to 8 to 12 million. And then we do a flat map, which essentially blow up of the tuples. Which essentially, like once we filter, these tuples are broken up into 5 times, so that the amount of data that is coming out is 40 to 60 million tuples per minute. And that is given to the aggregate bowl, which aggregates every 1 second, and it outputs around 25 to 40 million tuples per minute, writes it to Redis. Now let us see how the resource usage was. So Heron requested 120 resources to the scheduler, but the actual usage was 30 to 50 cores. And memory requested was 200 GB, but memory used was just 180. And the Redis, we had 24 cores requested, but hardly used 2 to 4 cores. And now zooming in, where the resources are actually going. So if you look at it, 84% goes into the spout instances. It's very unintuitive, where the data that we're fetching from Kafka or whatever it is, those are the ones which are taking the huge amount of time or the huge amount of resources. The bowls hardly do 9%, and Heron over is hardly 7%. So now profiling into spouts to figure out where the actual time is going. So we can see like the deserialized cost is 63%, and parsing and filtering takes 6%, and taking it out of the Kafka iterator as well as the Kafka fetch takes 16 plus 7, that is like around 26% or some, like 24 plus 3, 23%. So as it says, the fetching data, which is 63 plus 16 plus 7, that's close to 80 to 85% of the whole spout is gone to fetching data itself. If we eliminate that overhead, and if you take the raw binary, then we might even shave off all those things. So now profiling bowls, again, like going to writing data into Redis, that takes 68% of the data. Remember, the overall grand scheme of things, bowl is taking much more lower compared to spouts itself. Then again, serialization and deserialization takes around 20%, and some of the aggregation data transport takes only small amount of percentage. So effectively, like fetching data costs you more, like 61%, and usual logic takes 21%. Heron usage is 11%, and we have room in Heron to make it even 3x and 4x faster, but this is adequate enough to most of the processing at this point. So now one more numbers, like in terms of one of the topology that mimics production topology. It counts the real-time active count where people are interacting with Twitter. So some of the CPU usage, as you can see, the number of cores used versus Heron versus when you are at least once and at most once, the number of cores is significantly reduced in Heron itself. So the Heron overall saved like 3x to 4x worth of cost in terms of the number of machines and cores that we use. And if you want to learn more, so we have a bunch of papers. So Storm at Twitter, which was written in Sigma 2014, Sigma 2015 Twitter Heron. Then this is a new paper that's coming out. Then if you wanted to do a compendium of real-time analytics, so we did a tutorial in VLDB 2015. This is 180 slides of a lot of hardcore in-depth content. So if you are interested, please go and take, it's all available in SlideShare, so you can take a look at it. And that's all I had. I think I a little bit rushed, but hopefully everybody got the gist of it. Yes, please. Thank you.